Alright, as we continue in chapter 23, we move into a section of the chapter called The Plumber's View of Chromatography. Really all that means is that instead of looking at sort of the chemical aspects, the mechanisms of how things separate, we're going to look at the physics and the size of the tube and how fast it flows and what that means for different aspects of the separation. Okay, so getting into it, let's consider a column that has an inner diameter of 0.6 centimeters and a mobile phase that occupies 20% of the column volume. So there's those stationary phase particles, that powder occupies the other 80%. Okay. Well, we want to figure out a few things from this. The first thing that we want to figure out is sort of the volume of the column. If we knew the length of the column, we'd figure out the total volume of the mobile phase. But this doesn't give us the total length. So let's find the volume of the mobile phase per centimeter. The volume of any cylinder is equal to pi r squared h. And so we know pi r squared is just 0.3 centimeters squared. And I'm going to do this for every centimeter of column length. So my height is just 1 centimeter. And so I end up with a total volume of 0.283 milliliters. Okay, but I'm told that only 20% of that is actually the mobile phase. And so I'm going to multiply that by 20% to get a volume of 0.0565 milliliters. And again, that's my mobile phase. Okay. This is just an example. If you're given a problem where you know the whole length of the column, feel free to calculate the volume of the mobile phase for the whole length of the column. This example is from our textbook, and they didn't give us that, so we're just going to do it for 1 centimeter. Right. Now, if we know the mobile phase volume per centimeter of column, what we can do then is find the flow rate. The flow rate is one of the parameters that you can adjust in a chromatography experiment. And so again, this problem from our text tells us that the flow rate is 0.3 milliliters per minute. Okay. Now, if it's 0.3 milliliters per minute, what's the actual velocity of our mobile phase as it moves through that column? Often this is reported as a linear velocity. Linear velocity in that we only pay attention to the dimension that is the length of the column. And so the linear velocity is 0.3 mils per minute. And we're going to divide that by what we know is our volume. And so really what we're saying is that for every centimeter, there's 0.0565 milliliters of our mobile phase. Right? And so our milliliters here cancel, and we're left with 5.3 centimeters per minute. And so let's say we had a 10-meter column. It would take almost 2 minutes for the mobile phase to make it through the length of that column. Okay. All right. So more about how does this affect different properties of chromatography. As we look here, this is a chromatogram, and there are a few things that we need to keep in mind. Here we have our injection time. And so that's sort of our T0, our initial time for this analysis. For any separation, for anything that runs on a column, it's going to take some time for even just the mobile phase to make it through the column. Not to mention anything that you're actually trying to separate that might interact with the stationary phase, but just the mobile phase is going to take some time to make it all the way through the column. That time here is labeled TM, M for marker. And so in this example, methane is our marker. And so at this time, Tm, we see our marker come out. The assumption is that methane did not interact with our stationary phase at all, and that this time, Tm, is the time that it takes anything to move through the column, even if it doesn't interact with the stationary phase one bit. Another term, another name for this time is the dead time. Right? We're not going to get any peaks in that time because that's literally how long it takes anything to go through the column. Here we have an octane and a nonane and our unknown in the middle. The time that it takes to come off the column from the injection time to the peak is called the retention time. T sub R. You may have used this term when you did TLC chromatography in organic on the little plates. Same kind of idea. We're just not doing it at a column, we're doing it on a plate. The retention time gives us some information. Better information comes from knowing this T prime R. This is the corrected retention time. And this is just TR, well, T prime R is just TR minus Tm. This takes out any variance due to length of the column. Most columns that say they're 30 meters are 30 meters. But let's say that one happens to be 30 meters plus 5 centimeters, another one happens to be 30 meters minus 5 centimeters, right? There's some give and take there. If we correct for the time that the marker takes to get through the column, then we'll actually have a retention time that we can compare across all columns of the same variety. And so here in our corrected retention time, T prime R, it's just TR minus Tm. Okay. Another thing that we should keep in mind and that we can calculate here are the retention factors. And the retention factor is lowercase k, and that's equal to this corrected retention time divided by that dead time, that marker time. This will tell us sort of how much time a particular compound spends interacting with the stationary phase. If k was 0, right, so if k was 0, then Tr prime must be 0, which means that Tr is equal to Tm. If k is equal to 1, that means that Tr minus Tm must equal Tm if k is 1. And so if k is 1, then Tr equals Tm. And so, Tr prime is equal to Tm. So that would put our peak somewhere in here, right, for k of 1. And the longer it's on the column, the larger the retention factor. That just means that the more something interacts with the stationary phase, the more it's retained by the stationary phase, the longer time it's going to take to come off the column. So let's do an example here. We have a mixture of benzene, toluene, and methane that we inject into a gas chromatograph. Methane gives a sharp spike at 42 seconds, so that's going to be our marker. Right? And so I'm going to jot down here, Tm is 42 seconds. Our benzene required 251 seconds. Benzene, I'm just going to abbreviate BZ. And our toluene was 333 seconds. We're going to find the adjusted retention time and the retention factor for each solute. We are not going to talk about relative retention. It's in the textbook if you want to look at it. We are not going to worry about it for this part of the course. And so the T prime R for benzene is 251 minus 42, gives me 209 seconds. And Tr prime for toluene, 333 minus 42, 291 seconds. All right. So then we need to find K. K for benzene, let me do it over here. K for benzene is 209 seconds divided by 42 seconds. So that's 4.98. And K for toluene is 291 divided by 42. .93. So those are our adjusted retention times or corrected retention times and the retention factor for these two solutes. The relative retention is, of course, the ratio of these two retention times. It doesn't give us a whole lot of information aside from the fact that no matter what the column is, these two should have a similar relative retention time. So we have a 30-meter column versus a 10-meter column. Obviously, the retention times are not going to be the same, but the relative spacing of the peaks should be the same. And so that's more of an instrumental kind of quality of chromatography. If you take 411, I'm happy to talk more about that next fall. The last part of Chapter 23 that we'll take a look at deals with the efficiency of separation and how well separated two peaks are in our chromatogram. There are two factors that contribute to this separation. The first being the elution time between peaks. Okay. It's much easier for us to tell that two peaks are really two different peaks the further apart they are. Okay. The second is the width of a peak or the breadth of a peak. Let's say, for example, that I have two peaks that are relatively close together but relatively narrow, right? If I had to choose between these two, I would definitely choose this one, right? This is a better separation. Let's say I start with those same two peaks. Yikes, this is bad drawing. But in one situation, they're relatively narrow peaks. And in another situation, they're relatively broad peaks, right? It's hard to tell that that's really two different peaks. And so if we had to choose one, we would choose this one. Let me just sort of draw in here the fact that these are two peaks, they've just gotten very broad. So how do we know what's a good width and what's not a good width when it comes to a particular set of peaks? Generally speaking, the longer the retention time, the broader a band is going to be. Right? Part of this is due to diffusion. Right? The more time it spends in the mobile phase, the more it's going to try to, just random motion is going to cause it to not stay in that one packet, but move outside of that packet, broadening that peak. And so I go from having a peak that's like this to having a peak that's a little more like this, because yes, most of it is still there in the middle, but some of it has moved backward in the column, some of it has moved forward in the column. But how do we measure that breadth? There's really two schools of thought, and I'm sorry that my webcam's in the way here. The first is this W1 half, so that's when we measure at half the peak height. Another term for this is the full width at the half max, FWHM. And that's what we have here. Right? This is roughly the halfway point of our peak, and so they've measured the half width there. The other method, and really my preferred method, is to take the slope of the peak, right, that linear part of the peak, and just go all the way down to the baseline. Right? Here's our baseline, but there's our baseline. Extend that all the way across, and then we're going to do the same on the other side again. Sorry you can't see my webcam is in the way, but we have the width at the baseline versus the width at the top. This is giving values in sigma. That's standard deviation. We're not going to get into the statistics of these curves, but generally speaking, the width at the half width is obviously going to be narrower than the width at the baseline. And so we've talked about the two factors, the separation and the breadth, that tell us something about the efficiency of our analytical separation. And now that we've talked about how we define the breadth of a peak, the width of a peak, we're going to talk about resolution. That tells us sort of how good our separation really is. So resolution is given as a function of peak width. And so the one that I want you to know is the delta TR. Now TR prime, the difference between the two doesn't matter. But that's the difference in the retention time of the two peaks that we're interested in, divided by the average width. And so I'm just going to put WAVG. Right? If we look at this image, the blue is what we would actually see off the chromatogram. The black is the peak or peaks that make up that curve. And so if we look here, the blue that we see looks like a single curve, albeit very broad. Underneath, we see that there's really two peaks here. We have a peak here and a peak here. That delta TR is very small for those guys. And their width, we're going to come down here, their width is very broad. A short difference in retention time and a broad width gives us a very low resolution. Resolution of just 1/2. Here are examples where they get further and further apart. The one where I want you to pay attention is this one. Here, in between the peaks, we go down to the baseline. Right? We call that baseline resolution or baseline resolved. And also, when we get there, that resolution is 1.5. R has to be greater than or equal to 1.5 to be considered resolved. Right? Now, that doesn't mean that every pair of peaks that we consider to be resolved will have baseline resolution. In this example, these two peaks have exactly the same width, and that's a key piece of information. If one of these peaks was very narrow while the other was pretty broad, then they wouldn't need to be baseline resolved in order for us to call them resolved, in order for us to say, yes, I agree, that is resolved, and have a resolution of greater than or equal to 1.5. When we talk about column and how well a column can resolve, we talk about theoretical plates. This is a topic that comes up sometimes in P-Chem as well. But it's a big deal, especially in the distilling industry. When you distill a spirit multiple times, say vodka or a neutral grain spirit like Everclear, you want to separate the alcohol from the water as much as you can. And so there are physical plates that separate one distillation from the next. And so it's essentially like doing several distillations in one shot. Those are physical plates, and that's what is able to provide us with those very high strength alcohols. In chromatography, our columns are not made up of plates by any means, but we use what are called theoretical plates. So imagining that this were a plated column, how many plates would it have? The number of plates on a column is given by this retention time and the width. So it has something to do with how broad and how quickly a peak comes off a column. And so here we see N is equal to 16 times the retention time squared divided by W squared. Okay. Let's do a quick example. We have a retention time of 407 seconds, so that's TR. We have a width at the base, so that's W, of 13 seconds, and the column is 12.2 meters long. Find the number of plates and the plate height. And so let's see, the number of plates is equal to 16 times 407 seconds squared divided by W squared, 13 seconds squared. Now our units cancel here, but 16 times 407 squared divided by 13 squared, I got 15,700. I'm just going to give it 3 sig figs. 16,700 plates. That's a lot of plates. That's going to provide us pretty good resolution. When you go to a distillery that's making vodka, for example, maybe they have 5 to 30 plates, not 5 to 30,000 plates. If we want to know the plate height, this is usually given in centimeters, although it doesn't have to be. And the plate height is just equal to the length of the column divided by the number of plates, right? So how long our column is divided by how many plates we have. Right? Because it's usually given in centimeters, I'm just going to say that this is 1,220 centimeters, right? 12.2 meters, divided by our 15,700 plates. And so we get a plate height of 0.0777 centimeters, or we could put that as 777 microns, however you want to talk about it, right? This is the centimeters is the unit that I'm most familiar with seeing. Okay, so that's the end of chapter 23 that we will talk about. As we move into this instrumental stuff, there's a lot of material that we won't necessarily cover. I saved that for Chem 411, and so really pay attention to these lectures. And if you need some help to sort of pick up on a homework problem or something like that, you can read a little bit extra in the book, but don't get carried away thinking that you have to know everything that's in these chapters. Okay? If you need anything or if you have any questions, shoot me an email. We can Zoom. I'm happy to talk with you. Take care.